Imagine you're in a room filled with data scientists, analysts, and business leaders, all looking for the best way to make quick, smart decisions with data. The world of machine learning is packed with complex models, neural networks, deep learning, random forests, each promising high accuracy and deep insights. But what if I told you that sometimes the simplest approach can be the most effective? Meet the OneR algorithm, a method so straightforward it might make you skeptical. Just one rule based on one predictor, yet powerful enough to provide meaningful insights with minimal computation. Sounds too good to be true? Stick around, because what I'm about to show you will change the way you think about simple models in machine learning. But first, let's break it down. What exactly is the OneR algorithm, and why should you care? Picture this. You're sitting in a meeting surrounded by experts debating the pros and cons of machine learning models, neural networks, decision trees, ensemble methods. Everyone is throwing around names of algorithms that sound like they belong in a sci-fi novel. These methods are undeniably powerful, but often come with a steep price: complexity. They demand vast computational power, meticulous parameter tuning, and sometimes leave you with results that feel like a black box, difficult to interpret or explain. Now imagine a different scene, one where a single, straightforward rule can cut through the chaos and offer insights without overcomplicating things. A rule so clear that you can explain it to a colleague, a manager, or even someone without a technical background in just a few words. That's the essence of the OneR algorithm. It doesn't try to do everything. Instead, it hones in on one predictor at a time, crafting a simple rule that connects the predictor to the target variable in a way that is both logical and intuitive. Here's how it works. The algorithm generates a frequency table for each predictor in your dataset, examining how often different categories of the predictor correspond to specific classes of the target variable. From there, it identifies the most common or frequent outcome for each category and builds a simple rule around it. If X happens, then Y is the likely outcome. For example, if you're analyzing customer behavior, OneR might generate a rule like, if the customer is under 30, then they are more likely to purchase. It's a single, concise statement, yet it captures a meaningful pattern in the data. Why does this matter? Because simplicity is often underrated in the world of machine learning. We get so caught up in the allure of complex models that we forget the power of clarity and accessibility. OneR brings that back into focus. It doesn't require advanced computation, and the rules it generates are immediately interpretable, making it ideal for quick decision-making or when you need to explain results to non-technical stakeholders. But don't mistake simplicity for weakness. The OneR algorithm can hold its own against far more complex methods in certain scenarios, particularly when the data is clean and the relationships are clear. Its efficiency is unmatched. It doesn't bog you down with unnecessary computations or overwhelming configurations. Instead, it delivers actionable insights swiftly and effectively. Think of it like an experienced detective solving a mystery with just one clue. Instead of overloading their process with every possible detail, they focus on the most critical piece of evidence and make a decision based on that. The result, a solution that is precise, understandable, and surprisingly powerful. So, why should you care about OneR? Because not every problem requires a sledgehammer when a scalpel will do. In the right hands, this seemingly simple tool can uncover truths hidden in your data without the need for heavy machinery. It's a reminder that in machine learning and in life, sometimes less really is more. Are you ready to see how this single rule can make such an impact? Let's move forward and break it down. Now that we've introduced the OneR algorithm, let's dive into the first critical step: constructing frequency tables. Think of this as laying the groundwork for everything that follows. It's like preparing the ingredients before cooking a meal. You can't create something great without a solid foundation. Here's where the magic begins. The first task is to identify the predictor variable and the target variable. Imagine you're analyzing customer purchase behavior, and you have features like age, income, and purchase history. Your target variable is whether or not they made a purchase. To get started, you select one predictor variable, say age, to explore its relationship with the target. Next, you collect data and tally up the frequencies. This involves counting how many times each unique value of the predictor corresponds to each possible outcome of the target. For example, how many customers aged 18-25 made a purchase versus those who didn't. You're essentially gathering clues, one piece of evidence at a time. Once you have this raw data, you organize it into a frequency table. This table is like a snapshot of the relationship between your predictor and target. It includes the values of the predictor, the number of times each value appears, and how those values correspond to different outcomes of the target. Imagine rows showing how many 18-year-olds purchased versus didn't purchase, then how many 25-year-olds, and so on. Finally, you analyze the frequency table to uncover patterns. This is where the magic happens. You're looking for trends that stand out. For example, if 80% of 18-25-year-olds made a purchase while only 30% of 50-year-olds did, that's a pattern worth noting. This step is all about understanding which predictor values are most indicative of the target variable. At first glance, this might seem mundane, just counting things and organizing them into a table, but don't let the simplicity fool you. The insights hidden in these tables are the key to the OneR algorithm's power. They reveal the relationships that drive the single rule, helping you move one step closer to actionable insights. So, constructing frequency tables isn't just about crunching numbers, it's about uncovering stories hidden in the data. Are you curious to see how these tables transform into a single rule? Let's keep going and uncover the next steps. Now that you have built your frequency tables, it's time to make an important decision, selecting the best predictor. Think of this step as choosing the MVP, the one variable that has the most influence on predicting your target outcome. It's like being a coach and figuring out which player on the team has the best chance of winning the game. Here's how it works. The OneR algorithm evaluates each predictor in your dataset one by one and compares their performance in classifying the target variable. This performance is measured by a simple but critical metric, total error. Total error is calculated by comparing the predicted classifications based on the rules generated from the frequency tables to the actual outcomes in the data. The fewer errors a predictor makes, the better it performs. But this isn't just about minimizing mistakes. It's about accuracy, reliability, and interpretability. Accuracy matters because it directly impacts the predictive power of the final rule. The goal is to identify the predictor that produces the smallest total error, and in doing so, enhances the algorithm's ability to make consistent and meaningful classifications. Think of it like judging a competition where the winner isn't just the fastest, but also the most consistent performer. Let's make this real. Imagine you're analyzing a dataset with predictors like age, income, and education level, and your target is whether someone will buy a product. You generate frequency tables for each predictor and formulate simple rules such as if age is under 30, then purchase. If over 30, then don't purchase. For income, you might get if income is above 50K, then purchase, otherwise don't. By testing each rule against the actual data, you calculate the total error for each predictor. Now comes the exciting part, comparing the total error rates. The predictor with the smallest error wins the spotlight. In this example, if age results in fewer classification errors than income or education level, it becomes your chosen predictor, the one that will define your final rule. What makes this step so fascinating is that it blends precision with simplicity. You're not just looking for the most complex relationship, you're seeking the one that's both effective and easy to explain. It's a reminder that in machine learning, as in life, the best choices often strike a balance between performance and clarity. By the end of this step, you'll have your star predictor, the one that holds the key to building the most accurate and interpretable rule. Ready to see how this turns into actionable insights? Let's move on to the next phase. Now that you've selected your best predictor, it's time to craft the heart of the OneR algorithm, the rule itself. This step is where your hard work in building frequency tables and selecting the best predictor comes together to create something actionable. Think of this as turning raw ingredients into a perfectly cooked meal. Everything has been prepared, and now it's time to serve. The first task is to use your frequency table to identify classifications. For each category of your chosen predictor, you determine the most frequent class of the target variable. In other words, you're asking, what outcome is most likely for each specific value of this predictor? Imagine you're working with a predictor like age, and your target is purchased. If your table shows that people under 25 are most often buyers, while those over 25 are not, that's your key insight for this step. Once you've identified the most common outcomes for each category, you use these insights to generate rules. These rules take the form of simple if-then statements. For example, if age is under 25, then purchased. If age is 25 or over, then not purchased. Each rule is based entirely on the data and reflects the patterns you uncovered during the frequency table analysis. It's direct, clear, and immediately understandable. But generating the rule is only half the story. The next step is to calculate its total error. You apply the rule to your data set and compare the predicted classifications to the actual outcomes. Every time the rule gets it wrong, predicting purchased when the actual outcome is not purchased, for example, that's counted as an error. By summing up these errors, you get a clear measure of how well the rule performs. Finally, you select the one rule that has the smallest error rate. This is the moment where simplicity meets power. The rule you've crafted becomes your model, the single decision-making framework that guides your predictions moving forward. What makes this process so elegant is its transparency. Unlike many machine learning models that feel like black boxes, the rules generated by OneR are human-readable and easy to explain. They let you see at a glance the logic behind your predictions. By the end of this step, you'll have a fully formed rule, a single powerful statement that captures the essence of your data. But how effective is it? Let's keep going to evaluate its performance. You've built your rule, and now it's time for the real test, evaluating its performance. Think of this as putting your algorithm on the stage and seeing how well it delivers in front of an audience. This step is all about understanding how accurate and reliable your rule is and where it might fall short. The first key metric to examine is accuracy. Accuracy measures the proportion of correct predictions made by the rule compared to the total number of predictions. For instance, if your rule predicts outcomes for 100 instances and gets 85 of them right, your accuracy is 85%. This tells you how well your rule performs overall and gives you confidence in its predictive power. A higher accuracy means a more dependable rule, one you can trust to deliver insights consistently. But as much as we love accuracy, we also need to confront its counterpart, error rate. The error rate quantifies the proportion of incorrect predictions made by the rule. If your rule gets 15 out of 100 predictions wrong, that's a 15% error rate. This metric is equally important because it highlights the weaknesses or blind spots in your model. A lower error rate means a stronger rule, but any errors it makes offer valuable clues about where the rule might need adjustment or improvement. Here's an example to bring it to life. Imagine your rule is, if age is under 30, then purchase. If age is 30 or over, then don't purchase. You apply it to a data set, and the rule predicts 90 correct outcomes out of 100 instances. That's a 90% accuracy and a 10% error rate. This suggests the rule is strong, but there's room to improve, perhaps by considering additional predictors or refining your data. What makes this step so critical is that it isn't just about numbers, it's about Interpretation. Accuracy and error rates aren't abstract percentages. They're a reflection of how well your rule captures the reality of the data. A high accuracy tells you that your rule aligns well with the patterns in the dataset. A high error rate, on the other hand, might indicate noise in the data or an oversimplification in your rule. By the end of this step, you'll have a clear understanding of how your rule performs and whether it's ready to be deployed or needs further refinement. It's a moment of truth, a chance to see the real impact of the OneR algorithm in action. Ready to take the next step? Let's explore its advantages and limitations. Now that you've seen the OneR algorithm in action, let's step back and appreciate why this method has stood the test of time. The OneR algorithm isn't just about simplicity. It's about delivering value where it matters most. Its strengths lie in its accessibility, interpretability, and efficiency, making it a powerful choice in the right situations. First, let's talk about simplicity. The OneR algorithm is as straightforward as machine learning gets. There are no complex equations or intricate configurations to worry about. This simplicity makes it incredibly beginner-friendly, offering an easy starting point for those new to data science. Think of it like learning to ride a bike with training wheels. It gives you confidence while still delivering results. By focusing on one predictor and one rule, it eliminates unnecessary complexity, allowing you to concentrate on the essentials. Next, we have interpretability, a feature that's increasingly valuable in today's data-driven world. The rules generated by OneR are crystal clear and easy to understand. For instance, a rule like, if income is above 50K, then purchase, otherwise don't, can be explained to anyone, from a technical team to a boardroom full of executives. This transparency builds trust and ensures that decisions driven by the algorithm are both defensible and actionable. And let's not overlook efficiency. The OneR algorithm is remarkably lightweight. It doesn't require massive computational power or endless hours of tuning. Instead, it gets straight to the point, analyzing each predictor and identifying the best rule with minimal fuss. Imagine working with a dataset of thousands of records. OneR can process it in seconds, where more complex algorithms might take minutes or even hours. This speed and simplicity make it an excellent choice for exploratory data analysis or when you need quick insights. Here's an example to tie it all together. Let's say you're a marketing analyst tasked with identifying the key factors that drive customer purchases. You don't need a complex neural network for this. You need a quick, clear answer. By running the OneR algorithm, you discover that age is the most significant predictor, and the rule it generates, if age is under 30, then purchase, gives you a starting point for building your campaign. It's fast, effective, and easy to communicate to your team. The advantages of OneR lie in its ability to do more with less. It's not trying to compete with deep learning models or solve every problem under the sun. Instead, it excels in scenarios where clarity, speed, and interpretability are crucial. But as with any tool, it's important to understand its limitations. Let's take a closer look at those next. While the OneR algorithm shines with its simplicity and efficiency, it's not without its shortcomings. Like any tool, its strengths in certain areas come with limitations in others. Understanding these limitations is crucial to knowing when and where to apply the algorithm effectively. One of the primary limitations is the simplicity of the model. OneR relies on a single predictor to make classifications, which can lead to oversimplification of complex relationships within the data. Real-world datasets often have interactions between variables that a single rule can't capture. For instance, in a dataset where age and income together determine purchasing behavior, OneR might focus on just age and overlook the combined influence of income. It's like trying to understand a painting by only examining one corner. You're likely to miss the bigger picture. Another challenge is the potential for overfitting. While OneR is generally robust, it can overfit to noise in the data, especially when the chosen predictor has many unique values or categories. Imagine you're working with a categorical variable like customer ID, where each value is unique. The algorithm might generate overly specific rules that perform well on the training data, but fail to generalize to new, unseen data. This can result in high error rates when the model is deployed in real-world scenarios. These limitations don't mean the OneR algorithm isn't valuable. Rather, they highlight the importance of context. OneR is best suited for scenarios where the data is clean, relationships are straightforward, and interpretability is a priority. It's not designed for datasets with highly complex interactions or noisy, high-dimensional data. Think of it as a scalpel, precise and effective for specific tasks, but not the right tool for every operation. Here's a practical example. Suppose you're analyzing customer retention for a subscription service. The dataset includes predictors like age, region, subscription type, and usage frequency. If usage frequency has dozens of unique values, OneR might overfit, generating rules too tailored to the training data. On the other hand, a more nuanced algorithm could capture interactions between subscription type and region, providing better predictions. In summary, the limitations of OneR remind us that no single algorithm is a universal solution. By understanding its boundaries, you can harness its strengths while knowing when to look elsewhere for more complex problems. The key is to match the tool to the task. Ready to see how OneR thrives in real-world applications? Let's explore that next. Now that we've examined the OneR algorithm's strengths and limitations, let's bring it to life with real-world applications. OneR isn't just a theoretical concept, it's a practical tool that has been successfully applied across diverse industries. Its simplicity, interpretability, and efficiency make it a go-to choice for solving specific problems where clarity and speed are essential. Let's start with healthcare. Imagine a hospital tasked with predicting the likelihood of a patient developing a certain condition based on key factors like age, BMI, and medical history. A study demonstrated that OneR could accurately classify diabetes risk using a rule like, if BMI is above 30, then high risk, otherwise low risk, achieving an accuracy of 85%. This straightforward rule empowers healthcare professionals to make quick, informed decisions, enabling early interventions and better patient outcomes. Now picture the marketing world. Marketers are constantly trying to understand what drives customer purchases. A retail company once used OneR to analyze customer demographics and purchase history. By generating rules such as, if age is under 30 and made a previous purchase, then likely to purchase, they optimized their campaigns. The result? A 25% increase in conversion rates and a 15% boost in overall sales within just 3 months. OneR provided actionable insights without the need for complex models, proving that simplicity can drive results. In finance, the stakes are high when it comes to predicting loan defaults. OneR has been employed to build credit scoring models using historical data. For example, a financial institution identified that a rule like, if credit score is below 600, then high risk of default, reduced default rates by 30% and improved profitability. The algorithm's interpretability allowed stakeholders to trust the results and implement them effectively. Education is another field where OneR shines. Schools and universities use it to predict student success based on variables like attendance, prior grades, and socioeconomic status. In one case, a school identified that students with below average attendance were at the highest risk of failing. This insight helped them implement targeted support strategies, improving overall performance and reducing failure rates. These examples illustrate how OneR thrives in scenarios where decisions need to be transparent, interpretable, and actionable. It's not about competing with deep learning or neural networks. It's about filling a unique niche where simplicity is an advantage. By the end of this step, you'll see that the true power of OneR lies not in its complexity, but in its ability to turn data into insights quickly and effectively. Let's keep going to explore even more ways to enhance its performance. A major healthcare facility was struggling with high patient readmission rates. Readmissions are costly, strain hospital resources, and often indicate gaps in patient care. The hospital needed a straightforward solution, something that could quickly identify at-risk patients without the complexity of deep learning models. That's where OneR proved its value. The challenge was clear: predict which patients were most likely to be readmitted based on key medical factors such as age, number of prior admissions, and underlying health conditions. The goal was to intervene early, reduce unnecessary hospital visits, and improve patient outcomes. The team applied the OneR algorithm to analyze thousands of patient records. Using frequency tables, they examined each predictor variable and identified which one had the strongest correlation with readmission. The results pointed to one key factor: the number of previous admissions. Patients with more than 3 prior hospital visits within a year had the highest probability of being readmitted. From this insight, the hospital generated a simple rule: if the number of prior admissions is greater than 3, then high risk of readmission. This rule became the hospital's guiding principle for early intervention. Whenever a patient met this criterion, doctors and nurses would provide additional follow-up care, offer specialized treatment plans, and ensure proper post-discharge support. The results were impressive. Within 6 months of implementing OneR, the hospital reduced readmission rates by 20%. This translated to lower costs, improved patient care, and a more efficient use of medical resources. Even better, the simplicity of the rule made it easy for doctors and administrators to understand and act upon without needing specialized training in machine learning. This case study highlights why OneR is such a valuable tool in domains where clarity and speed are crucial. While it may not capture highly complex interactions like deep learning models, it provides actionable insights that can drive real change. Now that we've seen OneR in action in healthcare, let's shift gears and explore how it's transforming the world of finance. A financial institution was facing significant losses due to high loan default rates. Every year, thousands of loan applications were processed, but many borrowers failed to repay, leading to financial instability. The bank needed a predictive model to assess credit risk effectively, but the existing methods were either too complex or too time-consuming for practical use. They needed a solution that was both fast and interpretable. That's when they turned to the OneR algorithm. The goal was to identify the single most important predictor of loan default. The dataset included various factors such as credit score, income level, loan amount, and employment history. The OneR algorithm was applied to analyze the historical loan data, creating frequency tables for each predictor and identifying patterns in default behavior. The results were clear. Credit score emerged as the strongest predictor. The algorithm generated a simple rule: if the credit score is below 600, then high risk of default. This rule alone provided a reliable and actionable way to assess borrowers. Loan officers could now make quick decisions without relying on complex models that required extensive interpretation. Once implemented, the impact was immediate. The bank reduced default rates by 30% within the first year, improving risk assessment processes and ensuring better decision-making for loan approvals. Profitability increased as fewer high-risk loans were approved and financial stability improved. The simplicity of OneR meant that loan officers, even without a technical background, could confidently use the model to guide their lending decisions. This case study highlights the power of OneR in financial risk assessment. While more advanced models exist, their complexity often creates barriers to real-world implementation. OneR provided a straightforward solution that was both interpretable and effective, proving that sometimes the simplest approach can yield the biggest results. With its success in finance, let's now explore how OneR is making an impact in marketing, helping businesses predict customer behavior and improve conversion rates. A leading retail company was struggling to improve its marketing strategies. Despite investing heavily in advertising and promotions, conversion rates remained low and customer engagement was inconsistent. The marketing team needed a way to identify the most influential factors driving purchases so they could target the right customers with the right offers. They needed a model that was simple, fast, and easy to interpret. That's when they applied the OneR algorithm. The dataset included customer demographics, previous purchase history, browsing behavior, and discount preferences. The goal was to determine which factor had the strongest influence on whether a customer would make a purchase. Using OneR, the team generated frequency tables for each predictor and analyzed which variable had the lowest classification error when predicting purchases. The results revealed a clear pattern. Purchase history emerged as the strongest predictor. The model generated a simple but powerful rule. If the customer has made a purchase in the last 3 months, then they are likely to purchase again. This insight transformed the company's marketing strategy. Instead of sending generic campaigns to all customers, they focused their efforts on recent buyers, tailoring promotions specifically for this segment. The impact was immediate. Within 3 months of implementing the OneR-driven strategy, the company saw a 25% increase in conversion rates and a 15% boost in overall sales. The marketing team could now allocate resources more effectively, ensuring that promotional efforts targeted customers who were most likely to engage. This case study demonstrates how OneR can bring clarity to marketing decisions. Instead of relying on complicated predictive models, the team leveraged a simple, rule-based approach that delivered actionable insights. By focusing on what mattered most, they optimized their campaigns and achieved measurable results. With marketing success in the books, let's now compare OneR to other machine learning algorithms and see where it stands in the broader landscape of predictive modeling. Machine learning is filled with a variety of algorithms, each with its strengths and weaknesses. OneR offers simplicity and interpretability, but how does it compare to more complex models like decision trees? Understanding the trade-offs helps in choosing the right tool for the right problem. OneR simplifies classification by focusing on a single predictor with the least error, making it computationally efficient and easy to interpret. This makes it a great choice for quick insights and datasets where one variable dominates the prediction. However, its reliance on a single rule limits its ability to capture complex relationships between multiple variables. If a dataset contains strong interactions between predictors, OneR might oversimplify the classification, leading to lower accuracy. Decision trees, on the other hand, break data into multiple layers of decisions, allowing for more complex decision-making. A decision tree evaluates multiple predictors at each stage, splitting the dataset into smaller and smaller groups based on the most informative features. This allows it to capture intricate patterns that OneR might miss. However, with increased complexity comes a downside. Decision trees can overfit the data, making them less generalizable to new observations. They also require more computational power and may produce models that are harder to interpret compared to the single rule approach of OneR. OneR is ideal for situations where interpretability and speed are crucial. It is particularly useful in exploratory data analysis, where you need a quick sense of which predictor is most relevant. It works well when a single variable is dominant in classification, providing immediate insights without overcomplicating the process. Decision trees, however, are better suited for datasets with multiple interacting features, where a single rule is insufficient. They offer higher accuracy but at the cost of increased complexity. Choosing between OneR and decision trees depends on the problem at hand. If simplicity, speed, and transparency are your priorities, OneR is a strong choice. If you need a model that captures complex relationships and maximizes accuracy, decision trees might be the better option. The key is understanding the nature of your data and selecting the model that aligns best with your needs. Now that we've compared OneR to other approaches, let's explore how to implement it in Python and bring these concepts to life with real data. Implementing the OneR algorithm in Python is a straightforward process that requires just a few key steps. Unlike complex machine learning models that demand extensive tuning and computation, OneR can be built using basic data manipulation techniques. The focus is on constructing frequency tables, identifying the best predictor, and generating a simple rule that classifies new data points effectively. The first step is to import the necessary libraries. Python's pandas library is essential for handling datasets, while NumPy can assist with numerical operations. Once the dataset is loaded, the data needs to be preprocessed. This involves handling missing values, encoding categorical variables, and ensuring that the dataset is structured properly. Since OneR relies on frequency counts, data cleanliness is crucial for accurate rule generation. After preprocessing, frequency tables are constructed for each predictor variable in relation to the target variable. These tables count the occurrences of each category and display how they correspond to different target outcomes. By examining these tables, the total error rate for each predictor is calculated. The predictor with the smallest total error is selected as the basis for the final rule. Once the best predictor is identified, the next step is to generate the one rule. This rule is formulated by determining the most frequent target class for each category of the predictor. For example, if age is the best predictor and customers under 30 tend to make purchases the most, the rule could be if age is under 30, then purchase. This rule is then used for classification on new data. To evaluate performance, the OneR model is tested against unseen data. Accuracy and error rates are calculated to measure how well the rule generalizes beyond the training dataset. If necessary, adjustments can be made by refining the frequency tables or reconsidering predictor selection. The beauty of implementing OneR in Python is that it can be done quickly and with minimal computational resources. Its simplicity makes it an excellent choice for exploratory data analysis, where the goal is to identify the most influential variable before diving into more complex models. Now that we understand the implementation process, let's explore how to visualize OneR's results for deeper insights. Visualizing the results of the OneR algorithm is essential for understanding how well it performs and identifying any potential weaknesses. While OneR is based on a single rule, visual representations can help illustrate the model's effectiveness, highlight misclassifications, and provide insights into the overall structure of the data. One of the most useful visualization techniques is the bar chart. Since OneR classifies data based on a single predictor, a bar chart can effectively display the frequency of each predicted class versus the actual class distribution. For instance, if OneR predicts customer purchases based on age, a bar chart can show how many customers under 30 were correctly classified as purchasers versus how many were misclassified. This allows for quick identification of any major discrepancies between predicted and actual outcomes. Another powerful visualization tool is the confusion matrix. A confusion matrix provides a clear breakdown of classification performance by showing the number of true positives, false positives, true negatives, and false negatives. By visualizing this matrix, it becomes easier to spot where the model is making mistakes and whether those mistakes are occurring more frequently in certain categories. For example, if the model is predicting too many false positives, it might indicate that the chosen predictor is not fully capturing the nuances of the dataset. Accuracy plots also offer valuable insights. By tracking how the accuracy of the OneR model changes with different subsets of data or varying parameter thresholds, it becomes possible to understand how stable and generalizable the rule is. A line graph depicting accuracy across different training set sizes can illustrate whether the model performs consistently or if accuracy drops significantly when applied to new data. These visualizations make OneR's rule-based approach more transparent and interpretable. They help reinforce the model's strengths by showing how well it performs, while also highlighting areas for potential improvement. While OneR is already an easy-to-understand algorithm, visual representation enhances its interpretability even further, making it an effective tool for communicating insights to both technical and non-technical audiences. With visualization in place, the next step is optimizing OneR's performance. While it is simple by design, there are ways to improve its effectiveness, and that's exactly what we'll explore next. Improving the performance of the OneR algorithm requires fine-tuning different aspects of the model, from data preprocessing to parameter optimization. While OneR is simple by design, there are several techniques that can enhance its accuracy, reduce errors, and make it more robust for real-world applications. One of the most important steps is feature selection. Even though OneR relies on a single predictor, ensuring that only the most relevant variables are considered can significantly improve its performance. By conducting correlation analysis or using feature importance techniques, it's possible to filter out weak predictors and focus on the ones that truly contribute to classification accuracy. Data preprocessing is another crucial factor. Cleaning the dataset by handling missing values and removing outliers helps prevent bias in frequency tables. Normalizing or standardizing numerical features can also improve the algorithm's ability to generate more meaningful rules. Since OneR relies on categorical data, encoding continuous variables into discrete bins can sometimes enhance interpretability while maintaining classification accuracy. Cross-validation is a useful technique for assessing the stability of the OneR model. Instead of relying on a single training test split, implementing k-fold cross-validation ensures that the model generalizes well across different subsets of data. By maintaining the distribution of classes across folds, stratified sampling further improves the reliability of performance metrics. Parameter tuning can also play a role in refining OneR's rules. Experimenting with different threshold values or adjusting the minimum frequency count for predictor categories helps avoid overfitting, especially when dealing with predictors that have many unique values. Setting constraints on category frequency prevents the algorithm from creating rules that are too specific to the training data and unable to generalize effectively. By implementing these optimization strategies, OneR becomes an even more effective tool for classification. While its simplicity remains its greatest strength, these refinements ensure that the algorithm delivers the highest possible accuracy while maintaining its ease of interpretation. Now that we've seen how to optimize its performance, let's explore how OneR scales in big data environments and whether it can handle larger datasets efficiently. As datasets grow larger, the computational demands of machine learning algorithms increase. OneR, while inherently simple, faces unique challenges when applied to big data scenarios. However, with the right techniques, it can be adapted to handle large-scale datasets effectively. One of the main challenges in big data environments is computational complexity. As the number of predictor variables and data instances increases, constructing frequency tables for each predictor can become time-consuming. Processing millions of records using traditional methods may lead to performance bottlenecks, making it necessary to implement optimization techniques. Memory limitations are another challenge. Large datasets may exceed the available memory, making it difficult to store and process frequency tables. Without efficient memory management, the algorithm may struggle to handle high-dimensional data. One approach to addressing these issues is data sampling. Instead of processing the entire dataset at once, representative samples can be used to generate frequency tables. By selecting subsets that maintain the overall distribution of the data, sampling can significantly reduce computational costs while still preserving the accuracy of the OneR model. Parallel processing is another solution. By leveraging distributed computing frameworks such as Apache Spark or Hadoop, the computation of frequency tables can be parallelized across multiple processing units. This allows OneR to handle larger datasets by breaking down computations into smaller, manageable tasks. Incorporating feature selection techniques can also help optimize OneR for big data. Since the algorithm focuses on a single predictor, reducing the number of candidate predictors minimizes the computational workload. Using automated feature selection methods ensures that only the most relevant variables are considered, improving both efficiency and accuracy. Despite these challenges, OneR remains a viable option for big data applications where interpretability and quick decision-making are priorities. While it may not be as powerful as deep learning models for highly complex datasets, its ability to provide clear and actionable insights with minimal computation makes it an attractive choice for exploratory analysis. As machine learning continues to evolve, OneR is being refined and adapted for larger datasets. Looking ahead, advancements in computational efficiency and algorithmic optimization will further expand its potential. Now let's explore the future of OneR and how it continues to be relevant in an ever-changing technological landscape. The OneR algorithm, despite its simplicity, continues to evolve alongside modern advancements in machine learning. While it may not have the same level of complexity as deep learning models or ensemble methods, its role in classification remains relevant, particularly in areas that value interpretability and efficiency. Looking ahead, several key trends are shaping the future of OneR, making it an adaptable tool for various domains. One of the most exciting areas of development is improving algorithm efficiency. Researchers are exploring ways to refine the construction of frequency tables, reducing the computational burden without compromising accuracy. Optimized implementations using vectorized operations and parallel processing are helping to scale OneR to handle larger datasets more effectively. As machine learning frameworks evolve, integrating OneR into faster, more scalable platforms will further enhance its usability. New applications across different industries are also expanding the reach of OneR. While it has traditionally been used in marketing, healthcare, and finance, emerging fields such as automated decision systems, fraud detection, and supply chain optimization are beginning to explore its potential. The increasing demand for explainable AI is fueling renewed interest in rule-based models, and OneR's transparent classification approach aligns perfectly with this movement. Ongoing research and development are focused on hybrid models that integrate OneR with other machine learning techniques. By combining OneR with decision trees, ensemble methods, or feature engineering techniques, researchers are creating more powerful yet interpretable models. These hybrid approaches aim to retain OneR's clarity while addressing its limitations, such as its reliance on a single predictor. With the rise of ethical AI and regulations demanding more interpretable machine learning models, OneR is finding new relevance. Organizations are recognizing the importance of explainability, particularly in high-stakes decision-making where black box models are not ideal. The need for clear, rule-based decision-making is increasing, making OneR a valuable tool for compliance, transparency, and user trust. As machine learning continues to evolve, simplicity will always have a place. While OneR may not be the most advanced algorithm, it proves that in certain scenarios, clarity, efficiency, and ease of use can be just as powerful as complexity. As we wrap up, let's summarize the key takeaways from everything we've explored about OneR and its role in modern classification. The OneR algorithm serves as a reminder that sometimes the simplest approach can be the most effective. While machine learning is often associated with complex models and deep learning techniques, OneR proves that a single rule can provide meaningful insights, especially when interpretability and efficiency are key priorities. One of the biggest advantages of OneR is its ease of use. Unlike more intricate models that require extensive tuning and computational power, OneR allows for quick, rule-based classification. It is particularly valuable for exploratory data analysis, where identifying the most significant predictor is often the first step in building more complex models. Its transparency also makes it an excellent choice in fields where explainability is crucial, such as healthcare, finance, and regulatory compliance. Despite its strengths, OneR has limitations. Its reliance on a single predictor means it may not always capture complex relationships within a dataset. While this makes it easy to interpret, it can sometimes lead to oversimplified models that lack the predictive power of more advanced techniques. However, in cases where one predictor clearly dominates, OneR remains an effective tool. Throughout our exploration, we've seen how OneR can be applied in real-world scenarios, from predicting patient readmissions in healthcare to optimizing marketing strategies and reducing loan default rates. These examples highlight that while OneR may not be a one-size-fits-all solution, it has a distinct role in machine learning and decision-making processes. As machine learning continues to evolve, OneR remains relevant, particularly as industries prioritize interpretability alongside accuracy. The rise of ethical AI and the demand for explainable models further reinforce its importance. While deep learning and ensemble models dominate complex tasks, OneR provides a reliable, fast, and easily understandable alternative for classification problems where simplicity is an advantage. The key takeaway is that machine learning is not just about complexity, it's about choosing the right tool for the right job. OneR proves that even the most straightforward algorithms can deliver value, especially when speed and clarity matter most. Whether you're a beginner looking to understand classification techniques or a professional needing quick, actionable insights, OneR is a valuable addition to your toolkit.